Let's analyze in detail the differential equation that describes the stochastic volatility process. The stochastic differential equation has two terms. The deterministic or drift term has a reversion to the mean form. Alpha, which is a positive constant, is the reversion rate. And sigma infinity, which is also positive, is the level to which the volatility approaches when the time goes to infinity, is the reversion level. The stochastic term, or the diffusion term, is proportional to the level of the volatility at time t. The proportionality constant, psi, which is positive, could be thought of as the volatility of the volatility. Let's look at a simulation of this process. In this demo stochastic volatility, we will perform a number of simulations of the stochastic differential equation for a stochastic volatility model. The model has a drift term that is of the reversion to the mean type, and then it has a diffusion term that is proportional to the level of volatility. Psi can be thought of as the volatility of the volatility. Here is the definition of the stochastic differential equation. The initial volatility is 0.5, the reversion level is 0.2, the reversion rate is 1/2, and the parameter chi is 0.1. A is a handle to the function that defines the drift term, and it has the reversion to the mean form. B is a handle to the function that defines the diffusion term, and it's simply psi times sigma, the level of the stochastic volatility. Let's perform the simulation. We start at t0 and simulate up to 20. We're going to simulate 1,000 steps and 100 trajectories. Here is the function called to the stochastic Euler integration code that performs the simulation. Here we were just calculating the average over each of the trajectories to compare how the trajectories are actually fluctuating around the mean. And here are the simulated trajectories. Basically, we see that in black we have the average. We start at 0.5, which is the initial value of the volatility, and eventually, asymptotically, we go to 0.2. In fact, we can plot in this graph the reversion level of 0.2. We see that this is where all trajectories tend to. And finally, the characteristic time for decay, which is 1 over the reversion rate. And that corresponds, the reversion rate was 0.5, so that corresponds to 2. If the time is measured in years, that would correspond to 2 years. So here is the simulation.